Here's a number nobody puts on a poster. Getting a single kilogram of payload to just 10% of the speed of light, using the most efficient chemical rocket technology humanity has ever built, requires a starting mass of propellant so large the numbers stop being intuitive almost immediately. Not because we haven't tried hard enough, because of arithmetic. 3 episodes into this show's running argument about why the universe looks so quiet, we've covered why we might not be listening right, why the clock might not have caught anyone up yet, and why complex life itself might just be staggeringly rare. Here's the 4th answer, and it's the strangest one, because it doesn't require anyone to be missing, wrong, or unlucky at all. It just requires the universe to be the size it actually is. This episode is about the first half of that problem, even getting anywhere at all. Not warp drives, not faster than light anything. That's next episode's argument. This is the boring, remorseless, entirely earthbound mathematics of trying to move mass across interstellar distances using the actual laws of physics we're stuck with. And it turns out the honest version of this story is stranger and more interesting than space is big and rockets are slow. Let's start with the part almost nobody puts in the headline. The fuel problem doesn't get better with better engineering. It gets worse. The accounting problem. The equation at the center of this problem was worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903, decades before anyone had built a rocket capable of testing it. Footnote 1. The rocket equation relates how much your spacecraft's velocity can change to 2 things: how fast your engine can throw exhaust out the back, and what fraction of your total starting mass is fuel versus payload. That relationship is exponential, not linear, and exponential is doing a lot of quiet, devastating work in that sentence. Here's what exponential actually costs you. Voyager 1, the fastest object humanity has ever launched into deep space, is currently traveling at roughly 17 kilometers per second, genuinely fast by any everyday standard and utterly, laughably inadequate for interstellar travel. Footnote 2. At that speed, reaching Proxima Centauri, the nearest star system to our own at about 4.2 light-years away, would take on the order of 75,000 years. Not a long mission. A civilizational relay race with no finish line any single generation would recognize. So the obvious fix is go faster. Here's where the rocket equation stops being a formula and starts being a wall. To meaningfully shorten that trip, to get to even 10% of the speed of light using a chemical rocket, the same basic technology that got Apollo to the moon, the mass of propellant required doesn't scale up proportionally with your target speed. It scales up exponentially because every additional bit of fuel you add also has to accelerate the fuel you haven't burned yet. A 2004 NASA technical assessment of interstellar propulsion concepts concluded that chemical propulsion is fundamentally incapable of reaching even a modest fraction of light speed within any reasonable payload-to-propellant ratio. The mass required simply spirals out of physical plausibility long before the target velocity is reached. Footnote 3. This isn't a matter of we need a bigger booster. It's the physics actively working against you the harder you push. In a way, no incremental improvement in engine efficiency meaningfully escapes. This is the part popular explainers tend to skip past on their way to the exciting stuff. Better engineering does not fix an exponential. A 10% improvement in engine efficiency does not buy you a 10% improvement in how far you can go. The curve simply doesn't work that way. You can improve the exhaust velocity, switch propellant types, refine every subsystem for decades, and the wall doesn't move nearly as much as the effort you put into it. It is, in the most literal sense, a mass energy accounting problem. There's a hard limit on how much energy you can practically carry with you, and chemical propulsion runs out of runway long before Proxima Centauri becomes a realistic destination. Fascinating. An equation with an exponential term will, by definition, eventually make every linear improvement irrelevant. It would be illogical to describe that as bad luck. It is, however, entirely logical to describe it as the wrong kind of equation to be arguing with. The thin silver lining. If the problem with chemical rockets is that they have to carry their own fuel, the obvious next question is, what if they didn't have to? That's the actual serious research question behind Breakthrough Starshot, a project announced in 2016 aiming to accelerate gram-scale probes to roughly 20% of the speed of light using a ground-based laser array, pushing against a lightweight sail, rather than carrying propellant on board at all. Footnote 4. No fuel mass problem, because there's no fuel. The energy stays on Earth in the laser array. Only the sail and the tiny probe attached to it actually make the trip. The math here is genuinely more favorable than chemical propulsion. A project roadmap paper published in 2016 laid out a plausible, if extraordinarily ambitious, path to reaching Alpha Centauri in about 20 years of travel time, rather than tens of thousands. Footnote 5. That's the headline number, and it's the one that makes it into most popular coverage. Here's what usually doesn't. The obstacles between plausible on paper and probe arrives intact are substantial, specific, and largely unsolved. Start with the sail material itself. To be pushed to a meaningful fraction of light speed by a laser without simply vaporizing, the sail has to be simultaneously ultra-thin, reflective enough to survive the energy density involved, and structurally sound enough to hold its shape under acceleration forces far beyond anything a spacecraft has previously experienced. Then there's the interstellar medium itself, the thin scatter of gas and dust between stars, which sounds negligible until you're moving through it at a meaningful fraction of light speed. A 2017 analysis modeling the electromagnetic and physical forces on a relativistic sail found that collisions with even microscopic interstellar dust grains at those velocities deposit enough energy to erode or potentially destroy an unshielded sail over interstellar distances, a problem nobody has yet demonstrated a practical shielding solution for. Footnote 6. And then there's the part that rarely makes the headline at all. Breakthrough Starshot's current concept has no deceleration mechanism. The laser array on Earth can push the sail up to speed, but there's no equivalent laser waiting at Alpha Centauri to slow it back down. The current plan is a flyby, not an arrival, a few minutes of data collection at close to a fifth of light speed. Then the probe continues on into the dark, past the destination, forever. That's not a failure of the concept. It's an honest acknowledgement of where the research actually stands, a real, funded, serious engineering program with a genuinely elegant solution to the fuel problem, and at least 3 separate, currently unsolved problems standing between genuinely elegant and actually works. The people problem. Say you can't wait for laser sails to mature, or you're willing to accept a multi-century trip instead of a 20-year flyby. That's the generation ship concept. A self-contained vessel large enough to support a population across dozens of generations, with nobody aboard at launch expected to survive to see the destination. It solves the propulsion problem by simply accepting more time. It creates an entirely different problem instead. How many people do you actually need to put on that ship for their however many great-grandchildren to arrive as a viable, functioning population rather than an inbred, genetically compromised remnant of one? Popular treatments of this question tend to grab a small, dramatic-sounding number and move on, a few hundred colonists, because that's what fits comfortably in fiction. The actual research disagrees with itself, which is worth sitting with honestly rather than picking whichever number sounds better. A widely cited 2014 study modeling genetically viable population sizes for multi-generational voyages, incorporating realistic assumptions about mate selection, generational turnover, and genetic drift over centuries, put the minimum robust population in the range of many thousands, not hundreds, to avoid a genetic bottleneck severe enough to threaten the mission by the time it arrives. Footnote 7. A separate 2018 modeling study, using different assumptions and allowing for careful, managed reproductive planning rather than random pairing, argued a substantially smaller starting population of roughly 100 could theoretically remain viable. A figure that has since drawn considerable pushback from population geneticists for underestimating how badly things go wrong in practice once you introduce the messiness of actual human behavior, disease outbreaks, and unequal reproduction rates across centuries of enclosed travel. Footnote 8. That range, from roughly 100 to multiple thousands, depending entirely on your assumptions about how disciplined and lucky several hundred years' worth of descendants will be about who has children with whom, is not a rounding error. It's the entire ballgame. Get the number wrong on the low end, and you're not sending colonists to Proxima Centauri. You're running a multi-century experiment in genetic decline that nobody aboard signed up for, and none of them can undo once the airlock closes behind the launch generation. If life finds a way to make it to the next star system, just bring several thousand people, apparently not a few hundred, because it turns out the universe does not offer a group discount on genetic diversity. And somebody 11 generations from now is going to have strong opinions about whoever did the math on the guest list. The cruelest loophole. Here's the part of this story that sounds, on first hearing, like the physics doing us a favor. Special relativity's time dilation effect means that the faster you travel relative to a stationary observer, the slower time passes for you relative to them. An effect so counterintuitive that Einstein needed a specific, careful thought experiment to make it land, and popular explainers have been reaching for versions of it ever since. Footnote 9. Push a spacecraft to a large enough fraction of the speed of light, and a journey that takes centuries from Earth's perspective could, in principle, feel like a matter of years or even months to the people aboard. The classic formulation, a ship maintaining a sustained 1g acceleration for half a journey and matching deceleration for the other half could, at least in the math, cross distances that take Earth frames centuries to traverse while the crew experiences a small, survivable fraction of that time. Footnote 10. That sounds like the loophole. It is not the loophole. It's a trade, and the honest version of this section is naming exactly what gets traded away. Time dilation doesn't make the trip shorter in any objective sense. It makes it shorter for exactly one reference frame, and that frame is the one leaving. Earth does not experience the shortcut. If your ship's crew experiences 20 subjective years reaching some star system a few hundred light years distant, Earth experiences the full few hundred years passing in the meantime, in real time, the entire way through. Everyone the crew knew is dead long before the ship arrives. Any message sent back reporting a safe arrival takes those same few hundred years to return, arriving to a civilization that has aged, changed, possibly forgotten why the mission was launched at all, possibly no longer exists in any recognizable form. There is no round trip in any sense that matters to the people who stay behind. The ship's crew gets their lifetime back. Everyone and everything connected to that lifetime does not come with them. And there's a final, quieter irony layered underneath that one. Achieving the kind of sustained acceleration required to get meaningful time dilation in the first place requires exactly the kind of enormous, continuous energy expenditure section one already established chemical propulsion cannot remotely provide. The solution to the time problem still runs straight back into the accounting problem. Relativity doesn't rescue you from the rocket equation. It just tells you what you get if you somehow beat it. If we were able to calculate, with precision, how much subjective time a crew traveling near the speed of light would experience relative to those who remain behind, I am considerably less able to calculate how a person is meant to feel about arriving somewhere alive, having outlived everyone who watched them leave. I suspect that gap is the actual point of this section. So what does that leave us? Add it up, and here's where the honest version of this story actually lands. Laser sails solve the fuel problem at the cost of a probe that can't stop when it gets there. Generation ships solve the multi-century problem at the cost of needing a population in the low thousands disciplined enough to outmanage genetic drift for dozens of generations in an enclosed vessel with no possibility of leaving. Relativistic time dilation solves the lifetime problem at the cost of severing any meaningful connection to whatever civilization sent you, in either direction, permanently. Every fix this episode has covered is real, grounded in either current engineering research or settled physics, and every single one of them solved its stated problem by creating a new one that's arguably worse. None of that, notably, has anything to do with whether faster-than-light travel is possible. This entire episode has stayed inside the boring, remorseless, entirely permitted rules of ordinary physics, sublight speeds, real engineering constraints, real published research. And even there, at the edge of what's merely difficult rather than physically forbidden, the honest answer is that reaching another star system and meaningfully returning from it, as anything resembling the civilization that sent you, may not be a solvable engineering problem so much as a fundamentally different kind of no. Which raises the actual question underneath all of this, the one next episode is built entirely around. Even setting travel aside completely, even if two civilizations never intend to send a single ship anywhere, can they ever actually reach each other at all? Not with a spacecraft. With anything. A signal. A handshake. A single moment of mutual awareness across the distance separating them. Because it turns out the speed of light isn't just slow. It might be a wall in a much stricter sense than too far to visit. And that's where this argument goes next. None of this is really about rockets. It's about scale, the specific, humbling scale of trying to move a few kilograms or a few thousand people or a single idea across distances the universe never designed to be crossed casually. We built cathedrals that took centuries to finish and called that ambitious. This is a cathedral that takes longer to complete than the civilization that laid the foundation is likely to still recognize itself by the end. That's not necessarily a tragedy. It might just be an honest description of what it costs to be a species standing at the bottom of a very deep gravity well on a planet in the 10% of the galaxy where any of this was even possible in the first place, looking up and wanting very badly to go see the rest of it anyway. Getting there is turning out to be the hard part. So, it's a Tuesday, and there's still a lot of universe left to look at, which we will be doing in the next episode.